Hello everyone.
Hello.
Yeah. So hello everyone. I am Syed Abdullah Zain. I welcome you all for this free webinar on finite element analysis organized by Makers Tech Innovation and Connect to Tech YouTube channel. So we are also streaming live on our YouTube channel Connect to Tech. So before starting with the webinar, I want to introduce today's speaker, Mr. Dominic Madier. So Dominic Madier is a senior FEA consultant having more than 20 years of experience in mechanical structural analysis. So he have advanced expertise in finite element analysis of static and dynamic problems for linear and non-linear structural behaviors on aerospace metallic and composite structures such as aircraft fuselage, wing, engine pylon, helicopter airframe, etc. Dominic Madier have conducted detailed finite element analysis for aerospace companies in Europe and in North America, Airbus, Dassault Aviation, Safran, Bell Helicopter, Aerospace, Pratt Whitney Canada and the subcontractors. So Dominic Madier have completed his master's degree in mechanical and aerospace engineering from Paul Sabatier University, France. So Dominic Madier is also the author of the book Practical Finite Element Analysis for Mechanical Engineer. He is also the director of FEA Academy, Canada. I welcome you, sir.
Hello.
Hello.
Nice to meet you.
Yeah, I welcome you, sir. You can start presenting your screen, sir.
Okay. Do you see my screen now?
Yes, sir.
Okay. Excellent. So it means I can start presenting, correct?
Yes, sir. You can start presenting.
Excellent. So here, this is the agenda of the presentation for today. What I want to cover, typically it's three subjects. It's what is finite element analysis, working with the FEA in mechanical and structural analysis, and finally how to learn FEA. And then we will conclude with a Q&A session. So it is my introduction. So Syed already did that. Thank you for that, Syed. So just to mention that I had the chance to work in finite element analysis in the aerospace industry since more than 20 years on a very advanced programs for Airbus, for Safran, for Dassault Aviation, for Bombardier Aerospace, for Pratt Whitney Canada. And thanks to finite element analysis, I had the chance to work on those projects. So let's start with what is FEA, the first part of this presentation. Here, I want to cover the methods for solving an engineering problem and the different numerical methods, and an introduction to the partial differential equation, and finally, what is FEA. So let's start with the definition. According to NAFEMS, the International Association for the Engineering, Modeling, Analysis and Simulation Community, engineering simulation is the use of numerical, physical, or logical models of systems and scientific problems in predicting their response to different physical conditions. So there are three methods available for engineers to solve problems. First, we have the classical methods. Then we have the numerical methods, and finally the experimental methods. So first, the classical methods are based on what we call the closed form solutions, and in some cases these methods give accurate results. And in structural engineering, stress analysis are based on equations of the classical methods, such as the strength of material and the theory of elasticity. I'm sure you know that. However, they are only applicable to very simple problems. For example, a cantilever beam or a simply supported plate, a torsion of a simple section, for example. So even if they have been employed intensively at the beginning of the 20th century, they are only used for structural problems with simple geometry and loading and boundary conditions. And the weakness of such methods is that as an engineer, you must make many reductive assumptions to render complex situations compatible with the equation framework. So you know that in the real world, problems involve cases with complex shapes, complex boundary conditions, and material behavior. So there's real cases cannot be solved using classical analytical closed form methods. So numerical methods have been developed to solve the more complex problems. So by making assumptions, you can employ the numerical methods to produce mathematical representation of real-life engineering situations to solve complex problems. So with the advent of powerful computers, the numerical methods are proven to be increasingly accurate and reliable in solving complex problems. So they are approximate, but assumptions on which they are based are less reductive than those of the classical methods. In other words, the assumptions of the numerical methods are closer to reality than those of the classical methods. And finally, we have the experimental methods, which are based on measurements performed on a physical prototype, but they are time-consuming and expensive in terms of money, I mean. Moreover, to obtain accurate results, several specimens must be tested. However, this method is useful for validating the numerical models. It is why those methods, the experimental methods are still used, even if we are using the numerical methods. So to summarize, let's compare the classical methods with the numerical methods. So for the equations, the classical methods and the numerical methods, the equations are exact. For the solutions, the solutions are exact for the classical methods, but they are approximate for the numerical methods. In terms of number of solutions, we can only use a few standard cases for the classical methods, while all the problems can be solved with the numerical methods. For the shapes, the boundary conditions, and the loading, we have to do simplifying assumptions when we use the classical methods. When we use the numerical methods, there is no assumptions to do on the shapes, on the boundary conditions, and on loading. They are treated as they are. And finally, for the material, only isotropic and only one material can be used for the classical methods. While for the numerical methods, all type of property and unlimited number of materials can be used. So here I want to present the advantages and the disadvantages of prototyping. First, the advantages of prototyping, the experimental methods, are the prototyping are reliable, well mastered, and they are trusted by the regulatory agencies. And on top of that, they are essential for the calibration and the correlation of the FEMs. The disadvantage are they are very expensive compared to FEA, and they are, as I said before, they are time consuming. And they degrade the competitiveness of the product by raising the design cost. And they cannot replicate all the conditions and environments the product will encounter during its life. It is a huge limitation for when we use the experimental methods. So we have different numerical methods. We have in reality four different numerical methods which are commonly used to solve the engineering problems. First, we have the finite element method, we have the boundary element method, the finite volume method, and finally the finite difference method. All these methods can be used to solve the same problems. However, substantial differences exist among the methods with respect to results accuracy, ease of programming, and computation time. When internal details are required, such as the stresses in a part, for example, the boundary element method gives very poor results. And because the reason behind that is because it only considers the outer boundaries. In this case, methods such as the finite element method, the finite difference method, or the finite volume method are preferred. The finite volume method can be used by solving stress problems, but usually they are used to solve CFD problem, the fluid dynamic problems. The finite difference method has a limitation when it is used with complicated geometry, assembly of different material components, and the combination of various types of elements, the 1D, 2D, and 3D elements. So, to solve complex mechanical problems, the finite element method is by far the best method in terms of accuracy and computation time. So these methods share a common point. They approximate the solution to the partial differential equations that govern physics. Here, I want to do a quick reminder about partial differential equation. Don't worry, I don't want to do a math course, but I want to explain that a differential equation is a mathematical equation that relates some function to its derivatives. And the differential equations are used in many fields of science and engineering. Why? Because they make it possible to link the functions representing physical quantities and their derivatives. And these derivatives represent the rates of variation of the same function. It is what is interesting here for the engineers. So from a mathematical point of view, a partial differential equation can be used to formulate phenomena described by functions with several variables. And in such a case, the equation will be made up of multivariable functions and their partial derivative. So a partial derivative is a function of several variables. Its derivative with respect to one of those variables, with the other held constant. However, only the simplest differential equations are solvable by mathematical expression that can be evaluated in a finite number of operations, also known as the closed form expressions. So it means that we can use we can solve the differential equation only not for all the problems. So while all the physical problems can be expressed mathematically as differential equations, not all differential equations can be solved analytically. Many differential equations do not have closed form solutions. It is the problem. But it is possible to find solution to a given differential equation without determining its exact form. Indeed, if a closed form is not available, the solution can be numerically approximated using computers. And it is why numerical methods have been developed to determine solutions with a certain degree of accuracy. So here, it conducts us to speak about the need for analysis. First, we have a real structure, which is characterized by its geometry, materials, properties, the boundary conditions. And we apply on this real structure excitation like force, pressure, acceleration, thermal effects, vibration, etc. A lot of different types of excitation. And the objective is to obtain a response like displacements, forces, stresses, strains, natural frequency, etc. So the need for analysis comes from the fact that the FEA analyst must determine the structure response under given excitations to ensure that the design of the structure can sustain such excitations. And this gives us the need for modeling. The continuum nature of the problem and of the governing equations means that the real structure cannot be analyzed as is. Only a model of the structure can be analyzed by the computer. The FEA analyst, therefore, requires a tool with which to model the structure and analyze the model. So the continuum problem is transformed into a discretized solution using the finite element method, a numerical procedure by solving partial differential equation associated with field problem. So the classical problem is a real structure governed by partial differential equation, not resolvable by a computer. By doing discretization, assumptions, equilibrium, stress-strain law compatibility, we obtain a finite element analysis and a structural model, which is governed by matrix equation. And the matrix equations is resolvable by a computer. So in structural analysis, the domain of interest is the solid mechanics. And the field variables are the displacements, the dependent variables. And they are governed by differential equations. And the boundary conditions are the specific values of the displacement at the limits of the analyzed system. So the finite element method is based on the following matrix equation. This equation, the general equilibrium equation, which defines the rate of the state of equilibrium of forces acting on the structure. So here, this general equilibrium equation is constituted by mass matrix, damping matrix, stiffness matrix. And those matrices depend on the geometry and the material of the system we want to analyze. And we have to solve this equation for the displacement vector, the velocity vector, and the acceleration vector. And this on this part of the equation, we have the excitation, which can be a static effect or a dynamic effect. And we derive 4 different equations from this general equilibrium equation: the static analysis equation, the buckling analysis equation, the vibration analysis equation, and the transient and frequency response analysis equation. So while you may not be able to determine how a complex structural piece will behave, you can do so for a simple part of it. So it is why FEA is based on the following idea: divide and conquer. So if you divide a structure into multiple elements, the behavior of an individual element will provide a good approximation of local behavior, like, for example, the displacement, the stress, and the strain. So to be able to make simulations, a mesh consisting of up to millions of small elements that together form the shape of the structure is created. We call that the discretization or meshing. I'm sure you already hear those terms. And calculations are made for every single element. And combining the individual results gives us the final behavior of the structure or the system. So this means that we obtain the result at certain points within the structure, but not at every point. It is the key of the discretization. And the certain points are called nodal points and are located at the boundary of the elements. And the accuracy with which the variable changes across the elements is expressed by interpolation over the elements using polynomials. They can be linear, quadratic, or cubic. So the global assembly of the individual elements will reflect the behavior of the total structure. So if you assemble enough of these simple pieces, the elements, you can determine how a complex structural piece will behave. So it means that a good discretization, a good meshing is a question of balance. The more elements you use to represent your structure, the more precise and realistic the response you will get. But be careful, because nothing is free. The more elements you will use to represent your structure, and the greater the calculation time to solve it. So the key term is discretization. Discretization or meshing permits to transform a continuum problem into a discretized solution. So from a continuous system, which is the reality, defined by an infinite number of points and an infinite number of equations, you obtain a discrete system, the model, defined by a finite number of nodes and a finite number of equations. Here, an example for a simple plate with a hole, discretized with a finite number of elements. Here, another example of a fitting you want to analyze under tension is discretized with 3D element with finite number of elements. Here, a complete aircraft, again discretized with a finite number of elements. But here is a very with a lot of elements. With each substructure of the aircraft is meshed with the finite number of elements. The example of an engine, again with a lot of finite number of elements. So to summarize this first part of the presentation, what is FEA here? It's a graph. To understand what is FEA, you have to understand the following 4 key points. The element, first, a small section of the analyzed part. Each section is called an element, and each element acts on its neighboring elements. FEA assembles the equation from all the elements into one large matrix equation, and the numerical solution is determined by a computer. And you have the governing equation, which describe how each element behaves. So finite element analysis solves these equations for the analyzed physical part, depending on how it is held and loaded. And you have the finite term. Finite here represents the countable number of elements. It means that it is the discretization. And finally, you have the analysis. The analysis represent a static analysis, a dynamic analysis, a modal analysis, a buckling analysis. It can be linear or non-linear. So this concludes this first part, what is FEA, and now I want to explain how to how we can use FEA. What are we doing with FEA? How do we work with FEA? So how FEA can help you? What is the FEA process, and what are the capabilities of the FEA packages? And a very important point is how accurate is FEA, and why do FEA? And finally, what is needed to perform an FEA simulation? So let's start this part by how FEA can help you. FEA is helpful for all specialists involved in the product development. So first, it can help the stress and the structural engineers, then the dynamics engineers, and then the loads engineers, the engineers who define the load applying on the structure, and finally the designers, because it can help the designer to evaluate a lot of different configurations. So FEA can assist all the specialists in developing the parts, the different components of a product, and it helps them to make decisions during all phases of product development and to answer different questions. For example, will the product break? It's very important. Will the product deform too much? Will the product all together? Here I mean the different component of the structure, because the different component of the structure usually they are assembled with the fasteners, for example, or with welding, and it can help the engineers to answer the question: where are the weakest point in the structure? And can it be lighter? For example, in aerospace industry is very important. The weight of the structure is very important. So FEA can help you to define and to optimize the weight of the structure. And it can help you to define if it can be stronger and more durable. And it can help to define if it will work the way it was designed to. So here I want to give you seven situations where FEA can help you. First, FEA is used to solve complex problems of engineering and is useful for problems with complicated geometries, complicated loading, and different type of material properties in which analytical solutions are not applicable. Here, it's a very important point because the powerful of FEA is based on the fact that it can solve very, very complex problems that the classical solutions cannot solve. You can employ also FEA in multi-physics problems to provide solutions that would otherwise be impossible to solve with classical methods, because classical methods cannot mix different physics, while FEA can mix different physics. It is what we call multi-physics. With FEA, you can predict the response of mechanical structures to environmental factors such as forces, pressure, temperatures, vibrations, and you can combine them in the same simulation. Also, for engineers, FEA is an important part of the product design phase in an iterative development process, because it saves engineers time and reduces the effort and cost associated with building physical prototypes, because you will use a computer to evaluate different conditions without the need to build a physical prototype. You will build your physical prototype only at the end of the product development. During the product development process, simulation packages that have FEA functionality are used to determine the deformations and the stresses the component will undergo when subjected to environmental factors. Another situation where FEA can help you, the FEA packages are extremely powerful when used intelligently and help the engineers to define the critical dimensions of a component by considering the factors of safety, weight, and other parameters. And finally, FEA can be as simple as addressing a single part for which you wish to capture the behavior, but in the reality, it can also be used for more complex systems. Indeed, complex analysis may involve multiple parts for which you wish to determine the interactions. And most of the time, a structure is composed of various parts, various pieces, which are connected together, which are assembled. And FEA can help you to evaluate the connectivities between all those parts. So here, I want to share with you the common cases where FEA is used by engineers to solve complex problems. First, it is used for structural strength design, like cars, aircraft, bridges, a lot of structure, very complex structural structures. It can be used also for structural interaction with fluid flows, in acoustics problem, for thermal analysis, for vibration, and also for crash simulation. For fluid flow, we call that CFD. For buckling problems, it's typically instability problems. But also for dynamic problems, like frequency response, transient, random analysis. But also for electromagnetic evaluation, and also for metal forming. So it's a lot of applications. So FEA is useful at every stage of product design. It is the powerful of FEA. Before to define the product, FEA helps the engineer create a feasible design. After the product is designed, FEA permits the validation of the defined design. And finally, after the product is released, is on market, the FEA can be used to investigate product failures in order to improve the product. So at the end, finite element analysis permits the engineers to make great products, better products, by delivering better design quickly, which you cannot do with classical methods. So the FEA process from the engineer's perspective has to be understood. When an engineer is working with FEA, he has to follow a basic process. So first, he has to start with discretization. It is the selection of the element types and the creation of the meshing on the physical components from the CAD. And then he has to apply geometrical and material properties on the model and apply the boundary conditions, which dictate the behavior of the system at its boundaries. It's important because we have to define that in order to obtain a solution of the matrix equations. And then we have to apply the environmental factors, the forces, the pressure, the thermal effect, the vibrations on the system we want to evaluate. And then we solve the model by satisfying the equilibrium equations. So this is a process from the engineer perspective. But we have the process also from the solver perspective. So for the solver, it starts with an evaluation of the stiffness matrices of the individual elements of the meshing. And then the solver assembles the global stiffness matrix of the analyzed system. Then apply the load and boundary conditions, solve the equilibrium equations to obtain the displacement, and finally calculate forces, stresses, velocity, acceleration, strain, energy, all the outputs that the engineer needs to do the analysis of the system. So here, I want to present you what the commercial FEA software can solve, because they can solve a variety of single and multi-physics problems, including structural problems, and issues of heat transfer, fluid dynamics, acoustics, magnetism, and electric fields. Structural engineers use FEA to ensure that a structure has the necessary strength, stiffness, or life to prevent failure. For example, excess stress, resonance, buckling, or detrimental deformations that may compromise the structural integrity. So here, this slide shows you the various capabilities with the associated outcomes when engineers are using FEA. So you see, it's a lot of FEA capabilities. We have the FEA capabilities for linear static, for linear buckling, for nonlinear static and buckling, also for normal mode, linear dynamic, and nonlinear dynamic. So I don't want to go in detail here. I will make available this presentation to you, but you see, it's a lot of capabilities that the engineer has at his disposal for doing a lot of analysis. Here you can see on the other end all the FEA outcomes for static and buckling and for dynamic. It's also a lot of outcomes which help the engineers to do the finite element analysis. So the question here, which is important to answer, is how accurate is FEA? Because as a structural engineer, you will perform finite element analysis to predict the approximate response of a structure under a given excitation. So a legitimate concern is the accuracy of the prediction. First, the accuracy of the prediction will depend on the differences between the real structure, the reality, and the finite element model. Obviously, a perfect match is impossible because many assumptions are made when the structural model is built. For example, a first assumption is made on the CAD when it is discretized by creating meshing of the different parts that compose the structure. It is the first approximation. And the assumptions are made for the modeling of the joints. As I said before, the parts which compose a structure has to be modeled the fastener has to be modeled. So you will have to do assumptions of the modeling of the joints. You have to do some assumptions also on the material models. And the real loadings are discretized also to make them understandable by the finite element model. Assumptions about boundary conditions are made, and the analysts select the behavior the FEA will capture. So each of the assumptions will produce a deviation between the real structure and the finite element model. However, there is really no way to determine the real errors of the analysis. You can attempt to quantify the assumptions of the FEA to obtain a relative error. For example, analyzing boundary range of material properties would introduce error in the material response. For steel structures, this error is very small, since there is less than 1% variation in the modulus of elasticity of steel. However, when analyzing soil, for example, the error in material response could easily be 20%. It's an example. So the largest error in most FEAs is the result of bad boundary conditions. Incorrectly supporting your model can result in large errors that are transparent to the user. So FEA can yield spectacularly accurate results when compared with physical test results. Believe me, it's amazing how you can obtain very, very accurate results with a finite element analysis. However, in a complex FEA, it is still not possible to obtain an error of less than 1% in the whole model. Generally, a target of plus minus 10% global error allows for very good predictions. But this target does not prevent the occurrence of errors of less than 5% in some local regions of the FEA. So to produce a highly accurate FEA, the analyst has to pay attention to many points and perfect them, especially if the model is composed of several assembled parts. A single component model will easily match the real life, while a complex assembly will require more effort. But it's still possible with a complex model to have a very accurate representativity. So why do FEA? The most common advantages of conducting an FEA during product development are a capability to model complex systems, the reduced development time, the analysis of different design configurations, the performance and the cost optimization. Also the reduced testing, the safety improvement, the faster achievement of the required quality, the improvement of data available to engineers in decision making, and a better understanding of all components of a system, allowing for a more rational design. So it's a lot of advantages of conducting FEA. So what is needed to perform a structural FEA? As an FEA analyst, you must define a lot of things to build a finite element model that represent the physical problems. First, you need geometry, then you need properties, then you need materials, then you need loads, and finally boundary conditions. So this leads me to the last part of this presentation, which is learning how to learn FEA. So here, in this part, I want to present the 3 stages of the FEA learning process, the main rule of the FEA learning, and what is the main danger of FEA. And also, what do you need to learn in the FEA field, and my 10 guidelines for the FEA learning. And finally, I will conclude with the 5 advantages of learning FEA. So let's start with the 3 stages of the FEA learning process. The first stage is learning basic.
Hello.
Yes.
Sorry to disturb you, sir.
Yeah, hello.
Can you please share your screen, sir?
Okay. You don't see the screen?
Yes, sir. It's not visible.
Okay. It's since when? It's
5 minutes, sir. Like 5 minutes.
Oh, sorry for that. So let me. Okay, it said to me that it's sharing. I cannot. I don't have access to the sharing now. That's strange. I don't have access to the share button.
Just a second, sir. I'll check it.
Let me know when you see the screen.
Yes, sir.
You see the screen?
No, sir. Yeah, sir. It's now visible.
It's visible now?
Yes, sir. It's visible now. Just a second. I'll connect it. Yeah, sir. Again it went, sir. Hello.
Yeah.
Sir, can you please share your screen again?
Okay. Yes. But I don't have access to the share button.
Just a second.
Okay, I think, okay. You should see my screen now.
Yes, sir. It's visible now.
Okay. Let me know when.
Yes, sir. You can
when I
start
can
continuing,
continue.
sir.
Okay, thank you.
Yeah, fine.
So here, yeah, it is the last part of this presentation, how to learn FEA. So here I want to present you the 3 stages of the FEA learning process and the main rule of FEA learning, and also what is the main danger of FEA. And also I will present in this last part what do you need to learn in the FEA field, and my 10
Excuse me, sir, your presentation is not visible, sir.
FEA learning. And finally, I will conclude with the 5 advantages of learning FEA. So let's start with the 3 stages of the FEA learning process. The first stage is learning basic FEA theory, and then learning proper modeling techniques, and then learning how to use an FEA software. Engineers typically learn FEA theory in university or college before they learn how to use FEA software. And all too often, they skip the stage 2, which consists of learning the proper modeling techniques. For me, such an approach is problematic because many FEA analysts make incorrect assumptions and generate wrong analysis simply because they are unaware of the basic FEA rules. So good knowledge of proper modeling techniques will permit you to make the right assumptions and choices to accurately model and solve problems using simulation. And keep in mind that once you know the theory and the proper modeling techniques, learning an FEA software package is the easiest step in the process. So this leads us to the main rule of FEA learning. Learning FEA is more than learning how to use a software. It is more a question of understanding the FEA process, acquiring the best modeling practices, and knowing the behavior of the system you wish to model. And unfortunately, and all too often, as I told you before, engineers try to learn FEA by attempting to use the software before they understand the theory and proper modeling techniques. Personally, I strongly believe that learning FEA from a software perspective is a recipe for disaster. This is because FEA is not just about the software. It requires an understanding of the modeling process that allows you to solve physical problems. So the importance of the FEA software itself is very often overestimated compared with a good understanding of the modeling process. And during my coaching with the beginners in FEA, I realized that they focus on the graphical aspect over engineering data and modeling techniques. So what I want to suggest is always remember that an FEA software is just a black box for solving very complex systems of equation that you cannot solve by hand. And keep in mind that FEA is simply a tool used to help your structural analysis. So if you do not master the modeling techniques, you will likely submit an incorrect system of equations to the solver. But the problem is that the solver will give you a solution. And even if your system of equations does not correspond to your problem. So what is the main danger of FEA? The main danger of FEA is not knowing whether an answer given by the FEA software is correct or not. So always keep in mind that the FEA software gives an answer to a system of equations submitted by the analyst, even though the system of equations has nothing to do with the real problem. So to address this issue, you must follow the best modeling practices and use validated modeling techniques. You must understand the real behavior of the mechanical system you wish to model and be able to predict its behavior before beginning your modeling work. So it means that the most important quality you need before modeling a mechanical system using FEA is your engineering judgment. It is your favorite tool. So let me present you in 13 points what you need to learn in the FEA field in order to build reliable and accurate finite element models. First, you need to define an FEA strategy. I like to say that developing an FEM, it's like playing chess. You must anticipate problems, predict behavior, and adapt your strategy. So anticipating potential problems, potential issues when building a complex FEM involving multiple connected parts, it's not easy. So planning is the key. Without planning, you may encounter problems you will be unable to solve without diminishing the intrinsic quality of your problem. So you have to adapt your strategy to each simulation, to each problem you will have to solve. So for me, this first point is very crucial. Define an FEA strategy. It is the first thing you have to learn. Then you have to learn how the solutions available, you have to know the solutions available with your solvers. We have to know the capabilities and the limitations, because when you will use a solver, you will use linear solver, nonlinear solver, solver to solve static problem, buckling problem, dynamic problem, and each solver comes with capabilities and limitations. So you have to learn these capabilities and these limitations. Then you have to know the library of elements corresponding to your solvers. The library of elements, it comes with discretization. We know that with the nodes, the elements are the key of the discretization in FEA. Discretization, I mean the meshing, okay? The elements you will choose to build your model will influence its behavior. It is why the FEA software publishers document the library of elements associated with their solvers. So the capabilities of each element need to be understood by the analyst in order to select the right elements corresponding to the need. Personally, when I change my FEA solver, the first thing I do is to read the documentation related to the library of element in order to know the capabilities and the limitations of each type of element. Then you will have to learn how to perform meshing. When you perform meshing to do global FEM to capture global effect, or detailed FEM to capture local effects. So to be able to create a discretization, a meshing, compatible with your problem, you will have to learn a lot of things. Define a meshing plan, select the appropriate elements type to properly represent the behavior of the structure, to apply the proper mesh refinement, the mesh density, conduct the mesh conversion study, create the mesh transitions, perform the mesh quality checks, and choose between 2D and 3D meshing, and choose the element size. So it's a lot of things you will have to learn in order to be able to produce a good meshing. Also, you will have to learn how to define the boundary conditions. By boundary conditions, here I mean defining the constraints and the loading you will apply on the model. And believe me, it is one of the most complex problems you will have to solve as an FEA analyst. You have to know that the boundary conditions influence a lot the results. But keep in mind that the case, in most of the cases, even if you choose the wrong boundary conditions. So defining the correct boundary condition ensure that you submit the right set of equations to the solver. I mean the equations which correspond to your problem. And then you have to choose the right material models, because depending on what you analyze, a lot of material problems can be, material model can be selected. It can be a linear material, a non-linear material, it can be an isotropic, an hyperelastic, an orthotropic. So a lot of choices has to be done here. So you have to learn that also. You have to learn how to make the assumptions about connections. As I said before, most of the time you will have a system composed with several parts, and these parts are connected together. You have to model these connections. So you have to learn how to model these connections. You have to learn how to perform the validation and the correlation of your finite element model. This is a very important point, because it will give you confidence in your results, but also to your client and the final users of the FEA. There are methods available to validate your FEA, so you have to learn them and use them. And if you work with test data, you will have to learn how to correlate an FEM and how to adjust and calibrate your model. You have to learn how to understand the outputs provided by the solver. As I told you before, the FEA can produce a large variety of results, and you can extract them from the simulation. And you have to learn how to interpret them and how to make sure that they correspond to what you are looking for. You have to learn also how to perform some modeling. Some modeling is a very powerful method, because it's a modeling technique which will permit you to build very detailed analysis in a particular region of a model without the need to refine the whole model. And it's used a lot now to analyze very complex systems and very complex behaviors. And you have to learn also the optimization of the performance of your finite element runs, because there are parameters for each FEA package in order to optimize the performance of your simulation, and you will have to learn that. You will have to learn also how to document your FEA. It's important because from an industrial point of view, an FEA is associated with results, and it must be traceable years after the project is completed. So the FEA documentation has to represent the assumptions, to track the data used to perform the analysis, to provide the basis for further analysis, and to permit other analysts to replicate the analysis, and to permit training, and to establish the in-house expertise of FEA. So it's a very complex document. And finally, you have to learn and follow the best FEA practices. So let's go through my 10 guidelines for FEA learning. For a mechanical engineer, the FEA is one tool that is well worth of the effort to learn. Here, I want to provide you some tips that will help you in your learning process. First, for the structural analysis of mechanical systems, a strong background in engineering mechanics, including calculus, statics, basic dynamics, and strength of materials is required. You have to take classes in basic FEA theory. The better you know the basic theory, you don't know the advanced theory, but you need the basic theory as an engineer, because the better you know the basic theory being processed by the software, the more you will perceive the underlying limitation of the solutions. So what you have to learn is how the stiffness matrices are computed, how the global stiffness matrix of your system is assembled, how the solver compute the equations, and how the solver compute the secondary variables. At the end, knowing the basic theory will help you to make decisions during your modeling process. The third guideline I want to give you is do not begin with software. Learn FEA. The software enables you to build and examine the models, but it is dangerous to use it without understanding the underlying concept of modeling. Whatever software you use, the modeling techniques will remain the same. Okay? You have to in your learning process, you have to understand the behavior of your problem. Keep in mind that FEA is not employed to predict the behavior of your mechanical system. You must do the opposite and be able to predict the behavior of your structure to build a reliable and accurate FEA. Always try to understand the thing is depth. In the beginning, it takes time to understand the FEA process. However, there will be a profitable return on investment later, because by deeply understanding what occurs in one problem, you will be able to solve similar problems in the future. And it is interesting because it is interesting to understand the FEA in detail, and you need to go beyond the tutorial prepared by the software distributors, okay? Because such tutorials, typically they explain where to click to obtain the result of simulation. And by following such tutorials, you will obtain answers. You will press the computation button and likely obtain the result without ever seeing a single error message. But you have to know that this approach will not make you a real-world FEA analyst. So start with simple problems. It is always best to start with simple models. A building block approach is an efficient way to learn FEA. Studying simple problems initially allows you to truly understand what is going on, so that you can eventually solve complex problems faster. So the short run time of a simple problem is another advantage. With a simple model, if any part is incorrect, you will not have to wait long for the results of the error message. So you will be able to fix it quickly and iterate rapidly, and this will speed up your learning process. So start with simple problems. And take FEA training classes, because the FEA training classes, the FEA training class instructors are often specialists in the field, and they can provide a lot of practical knowledge. FEA training classes teach you much more than which buttons to push to create a solution. These classes will teach you the modeling techniques that you will be able to use for any problem you will face in the projects you will be involved and independently from the FEA software. This guideline I want to give you is practice, practice, and more practice. And let me tell you the word from a trainer at the end of an FEA class. You will have two choices: practice what you have learned, or I will see you next year for a repeat of this training course. So it's true, you have to practice a lot to master FEA. And join user group and attend any FEA seminar. User group, both online or in person, are a great way to learn from your peers. I strongly believe that other people are the best source of knowledge, and many more people than you think want to share their knowledge. So attending FEA seminars will also help you to stay up to date on the latest FEA features. And finally, the last guideline I want to give you is be patient, because it takes time to learn FEA. There will be a lot of trial and error, because before you reach the point where you feel confident about what you are doing. If you start from scratch and use good resources, it will usually take about 3 years to learn the basic knowledge. And you have to add 5 years to learn the advanced knowledge. But this doesn't mean that after 8 years you will have nothing to learn. FEA is a field that is rapidly evolving. Even after 8 years of practice, you will still be learning new things about FEA, because FEA is complex. So take it one step at a time. FEA is a very powerful tool that looks incredibly simple from the outside, but in reality it's not. FEA is complex and there is a lot to learn. Again, keep in mind that FEA always provides a response, even if it's an incorrect one. So if you don't have strong FEA knowledge, you may not recognize inaccuracy in the result. So you have to think of FEA as a calculator that is difficult to use. So take your time acquiring the necessary knowledge for conducting a good analysis, and you will be able to simulate and solve all the engineering problems you want. So before to go to the advantages in learning FEA and conclude, let me present you the wheel of FEA structural competencies from the Boeing company. This graphics show you all the competencies you need to have to masterize the structural design, the different structural design criteria. Here, on the orange portion of the wheel, you have the various design criteria you have to master to design a product. Linear quasi-static analysis, detailed FEA analysis, parametric CAE, optimization, probabilistic FEA, nonlinear geometric analysis, nonlinear material analysis, vibration and dynamics analysis, nonlinear explicit dynamics, multiphysics, fracture and failure analysis, virtual test. And for each criteria, you have the various skills associated with each. So you see, it's a lot of skills you need to acquire in order to masterize the complete criteria. Practically, the FEA engineers, they don't masterize all the criteria. So they are specialized in some criteria, okay? It's not possible to masterize all the criteria. You probably masterize 5, 6 criteria, not more. But I just want to show you this wheel, this graphic, because it shows you that it's a lot of skills you have to learn. So let's conclude this presentation with the advantages of learning FEA. First, learning FEA permits to solve complex problems. The main advantage of learning FEA is the fact that you can solve problems that are impossible to calculate otherwise. This is because end calculations based on classical analysis are only valid and accurate for very simple problems, not for complex problems. However, as a mechanical and structural engineer, you will rarely be faced with simple problems. Advanced designs are so complex that classical methods, such as end calculation, will not allow you to meet the objectives. So learning FEA gives you an edge over other engineers. Learning FEA gives you an edge over engineers because instead of using conservative assumptions to make an inaccurate end calculation work, you can simply use a computer to conduct FEA, to capture the real failure modes, and to compute the critical parts of your design in a multitude of different configurations. Moreover, with FEA, you can find solutions to problems driven by various phenomena such as elasticity, vibration, stability, plasticity, interaction between parts, what we call multiphysics. So by mastering FEA, you will be able to solve better products for a fraction of the cost and time. And another advantage of learning FEA is that it will permit you to avoid its dark side. Because yes, FEA has a dark side. The first aspect of this dark side is that it is very difficult to find errors in complex FEMs. So learning the verification process will help you to retain control of your models and give you greater confidence in the results. And the second aspect is that FEA can be used to prove wrong results by making bad assumptions. So by learning FEA in detail and mastering the modeling techniques, you will avoid such pitfalls and you will be a better FEA analyst. And FEA improves your versatility. The flexibility of FEA is such that it can be used in various applications. And engineers with very good knowledge of FEA is much more versatile than one who does not know it very well. So since the modeling techniques are universal, mastering FEA will permit you to navigate various types of industry and work in different projects. And to conclude, I want to mention that everyone can learn FEA. Just follow the 3 stages in the right order. But please don't miss the step 1. Learn the modeling techniques before an FEA software. The last thing I want to share with you is that with FEA, you will never stop learning something. It is the beauty of this discipline. So before to jump into the Q&A session, let me present you my book. It's a practical finite element analysis for mechanical engineers. It's more than 650 pages of modeling techniques, of guidelines and method to learn FEA. And it's illustrated with more than 100 examples, and it's available in the bookstore of the FEA Academy website. And you can also find on the FEA resources on the FEA Academy website, like the files of the example illustrating the modeling techniques. And you will have also available free webinars, the replay of the free webinars on this website. So that's it for me. We can jump to the Q&A session if you want.
Hello.
Yeah, hello.
Yeah, thank you, sir. Sir, there are some questions from the students which I want to pass on it to you.
Yeah.
Yeah, okay. So students are for the beginners. So which is the software which you recommend to use in finite element analysis for the beginners?
Okay, to be honest, there is no software for beginners, because all the softwares are the same. Okay, but we have three major softwares used in the industry. The three major softwares are Nastran, Abacus, and ANSYS. So I would say that at least 95% of the products are analyzed with the three softwares, let's say three solvers, because you have to understand that in finite element analysis we have two kinds of softwares. We have the pre-post processing software, which permit to create the machine, to create the model, and we have the solvers, which permit to solve the solutions. Okay, so Nastran, Abacus, and ANSYS are the solvers. For the processing, for the pre and post processing software, there are plenty of different softwares which are the same, and they are doing the same job. They are permitting to do the meshing, to apply the loading, to apply the properties, and so yeah, it is my answer.
Yes, sir. Thank you, sir. And sir, there is one more question from the student.
Yeah.
They wanted to know, like, how are the steps involved in the industry, like how the processes will begin and how it will be validated. So will there be any experimental analysis after following the numerical approach, or the data will be sent directly to the manufacturing industry after performing the analysis?
Okay, that's a very good question. Yeah, obviously, yeah, there are a lot of validations before to go to the manufacturing, because during the designing process, the analyzing process is embedded in it. Okay, so usually there is a design team and an analysis team, and the two teams are working together. So the analysis team help the design team to make sure that what has been designed will work in the real life by doing the FEA. As soon as the analysis has been done, sometimes, most of the times, there is a test campaign which is done on a prototype, okay, but only on one prototype. And this prototype with instrumentation permits to record how the product behaves in the reality, and it permits to validate the analysis. Okay, and as soon as the analysis has been validated with the prototype, then we can use the analysis to derive a lot of configurations, because since the analysis has been validated, since the FEA has been validated by the prototype, we can modify the analysis to represent various configurations, various environments, in order to improve the product. And then we can go to the manufacturing process. This is the process. Does this answer the question?
Yes, sir. Thank you, sir. And there is one more question, sir. They wanted to know the difference between FEA and FEM, finite element analysis and finite volume method.
Okay, between FVM and FEM. Okay, good. So yeah, finite volume method. It's a method which is used to analyze computational fluid dynamic. It's used in aerodynamic to simulate the flow of fluid around a structure, while the finite element method is used in solid mechanics. It's a different numerical method. So FVM and FEM are two different numerical methods, okay? But they are based on approximating the solution of partial differential equations. But the numerical methods associated with each method it's different, and it's associated to two different domains. Finite element method is the solid mechanics domain, while finite volume method is the fluid domain.
Fine. Thank you, sir. So there is one more question, sir.
Yeah.
Sir, coming to the part, so there is a question. So if a part consists of multiple analysis, so which are the analysis which will be given preference and which will be carried first? For example, if a part is if the part is having application in thermal field, then computational fluid dynamics field, and in the structural field, so how the process will be started in the industry? Whether first it will be structural analysis and then thermal and any other analysis, or how it is, sir?
Okay, yeah, no, typically all these analyses are done in parallel. Okay, so we start with a basic design, and the basic design is analyzed in parallel in solid mechanics, in thermal, in fluid. Okay, and each analysis is conducted in parallel and give their output. From the output from each analysis, the design is modified or improved. Okay, and then we loop like that the number of time we need in order to obtain the optimized product, let's say. But all is done in parallel. For sure, all the different analyses can share the outputs, okay, in order to improve the analysis, but all is done in parallel. So it means that one analyst does not perform all the different analyses. There is an analysis team for the solid analysis, another team for the fluid, another team for the thermal. Okay, it's not one analysis team for all the different domains.
Thank you, sir. There is a question from some students, sir. Like most of the students have the same question. They wanted to know which are the important concepts to learn from FEA which will help them in interview.
That's a very good question. There are a lot of concepts to know. By an interview, you mean an FEA interview for an FEA position, correct?
Yes, sir.
Yeah. Okay. That's a good question, and I'm going to conduct a webinar Friday about that, and I collected the 50 most frequently asked questions during an FEA interview. And Friday, I'm going to conduct a webinar, and I'm going to give you my best answers. I mean, the best answer that the interviewers want to hear during an FEA interview. I cannot answer the question here because there are a lot of questions that an interviewer can ask you. Okay, so and there are many concepts. In many FEA concepts that the candidate has to master in order to succeed the interview. So I can give you rendezvous Friday to my free webinar. You can register on my free webinar for that.
Sure, sir. Thank you. So the webinar registration link will be shared to everyone.
Yeah. It is already published on LinkedIn. The link is already published, but I can send you the link if you want to share with your audience.
Sure, sir. Thank you, sir.
And it's a free webinar, so everyone can register. And at the end, all the registrant will have access to a replay to the webinar, and I will share a PDF document with the 50 most frequently asked questions with my best answers. So the people will be able to work to prepare the interview with my documents if they want.
And sir, there is one more question, the last question from a student. So are there any future opportunities in finite element analysis for mechanical engineers?
Yeah, there are a lot of opportunities, and the reason why it's because now finite element analysis is embedded in the product development process. It is a mandatory task of the product development product, and it's impossible to develop a product now without finite element analysis. All the products we are using in the real life are developed using finite element analysis. The reason why it's because finite element analysis permits to simulate all the different conditions, all the different configurations that the product will encounter in the real life. So finite element analysis permit to simulate that, and finite element analysis permit to obtain reliable products since the beginning. As soon as the products are released by the manufacturers, the product now are reliable and safe. And it is thanks to FEA. Without FEA, it's impossible. So there is a huge future for FEA in the various industries and in all the industries, because now all the industries are using FEA to develop their products. So the answer is yes, there is a huge future for finite element analysis. Personally, it makes more than 20 years that I'm doing finite element analysis in the aerospace industry, and I have seen that during the last 23 years, I have seen the increase in using FEA is dramatic. It's huge how FEA is used now to develop products.
Yes, sir. Thank you very much, sir. So I hope everyone have got their answers. So and before closing the session, I want to thank everyone for attending this webinar, and especially Dominic Madier sir for giving us his precious time, and we have learned a lot of details from it, and we hope this will be a useful webinar, and everyone can make use of it from this webinar. I once again thank you so much, sir. So the video of this particular webinar will also be available in the YouTube channel, and if anyone needed the recorded session, it will be sent it to their mail IDs. And I recommend everyone to read the book from Dominic Madier sir. Sir, do you want to say anything?
Yeah, I want to say thank you, Sayed, for inviting me to this webinar. I appreciate that, and I'm very happy to have done that with you today. And I want to mention that I'm going to send you the PDF document related to this presentation, so you will be able to share that with the attendees.
Sure, sir. Thank you so much, sir. And I would also like to get a link regarding your website and the book, so that I can share it with the participants. The link from which they can purchase and view the book.
Yeah, okay, good. Thank you very much for that, Sayed. I appreciate.
Yeah, thank you so much, sir. It was a nighttime